All right, everyone. So I am going to use this time to talk a little bit more about hybridization and how do you determine what hybridization an atom is within a chemical structure. Hybridization has to deal with the geometry of the molecule and the angles at which those atoms are linked together. So we have to think back to the electron geometry. And so I have this table here, and honestly, you could just affix this onto this extra column right here. I put hybridization onto your exam one, last page that you did. So if you have two electron domains, that geometry makes you linear. That molecule, those atoms are going to be in a row, 180 degrees, so they're linear. Excuse me, atoms that have only two total electron domains are going to be sp hybridized atoms. If you have a total of 3 electron domains, your geometry is trigonal planar. Remember, all 3 of the bonds are going to be in the same plane of the page. The angle there is 120 degrees. Atoms that are trigonal planar are sp2 hybridized. If you have 4 electron domains, your overall shape is tetrahedral, and your angle is 109.5. Those atoms are sp3 hybridized. If you have a total of 5 electron domains, you're going to be trigonal bipyramidal. And 3D. So now you're going to start to use some d orbitals. So remember this trigonal bipyramidal, and then the last one here is 6 electron domains octahedral. So trigonal bipyramidal and octahedral compounds are only going to be in the n = 3 or greater rows. The row that in at least the P block is aluminum, silicon, phosphorus, sulfur, chlorine, and down. Okay. But so if you have 6 electron domains, your overall shape is octahedral. You've got these 90-degree angles for all 6 of the atoms that are coming off, being attached to you. And this hybridization is called sp3d2 hybridized. So you're actually hybridizing your s valence orbital, all 3 of your p valence orbitals, and 2 of your d orbitals to allow for a total of 6 unique atoms to be bound off of you. All right, so if you want to, that's all you really have to know if you wanted to look at a structure and determine whether or not it's what sp, sp2, sp3, sp3d, or sp3d2 hybridized, is if you know if you can count the electron domains and determine what the geometry is, you can determine the hybridization. So when we are talking about atoms that have multiple bonds, for the sake of this class, we're only going to say atoms that are sp2 and sp hybridized are the only ones that can make multiple bonds. Again, we're going to focus on essentially the n = 2 row, which is like boron, carbon, nitrogen, oxygen, and fluorine. In order to make a double or triple bond, what you need is an unhybridized p orbital. If you recall from when we actually were looking at those energy diagrams, if you're thinking about your valence orbitals, you have 1 s orbital and 3 p orbitals. And if maybe I want to make an sp hybridized atom, I only take the 1 s and 1 of the p orbitals, and I hybridize them together to give me 2 sp orbitals. But then that leaves me with 2 unhybridized p orbitals. So those are the orbitals that can make those multiple bonds, the second and the third bond. So single bonds are going to be called sigma bonds. And when you have a double or triple bond, you start to call those the pi bonds. And so on the next screen here, we're going to identify some of the atoms, determine what their hybridization is, and talk about the types of bonds, sigma and pi, that are there. So I essentially have 2 structures I want to look at. I'm going to look at penicillin, and I want to look at this crazy structure I found online. I don't know what it is, but boy, it had a whole bunch of different hybridizations of the different atoms, and so that's what we're going to look at. First, when we look at penicillin, I'm going to zoom in here on this penicillin structure. remember, this is the structure. So when we see it, these oxygens, nitrogens, they don't usually contain their lone pairs of electrons. Recall back from, if you can spell honk and count to 4, you can do organic chemistry. Oxygen likes to make 2 bonds and have 2 lone pairs. So you can go in and fill in the lone pairs on the oxygens. This oxygen is making 2 bonds. 1 bond here, the other bond would be to that hydrogen. They just drop it when they're writing the structure here. But so that also is going to have 2 lone pairs. Nitrogen, if you can honk and count to 4. So nitrogen, it likes to make 3 bonds and have 1 lone pair. That lone pair is due to the nitrogen having 5 valence electrons. So it would be like 1, 2, 3, 4 would be bound to this hydrogen, and 5 valence electrons. There they all are. So again, nitrogens like to make 3 bonds and have 1 lone pair. And then lastly, probably the only other atom in here that's different, non-carbon, is the sulfur atom right here in this penicillin structure. Sulfur is under oxygen on the periodic table, so it follows very similar bonding patterns, which means it likes to have 2 bonds, and it'll have 2 lone pairs on it as well. All right. The other thing I wanted to mention, image, is for drawing skeletal structures, that carbon always makes 4 bonds. If you don't count or see a bond that adds up to 4 carbon atoms in here, the missing bond is to a hydrogen. My color real quick here, and let's go in and fill in all of the missing color, like purple, carbon atoms, and I'm going to start with this carbon right here. So if I count the bonds on this 2 bonds, so there's no missing hydrogens. If I come right here and look at the 3 bonds, so we are missing a hydrogen. So I could draw in a hydrogen right there coming off of him or her. If I look at this carbon atom right here, it already has 1, 2, 3, 4 bonds. So it doesn't need a hydrogen. Actually, this hydrogen, if I'm thinking stereochemistry, is coming out of the page because this bond is going back. And then these 2 are in the plane. So this is that tetrahedral shape with 4 things bound. So something's coming out, something's going back, and 2 are in the plane of the page. Let's see. Nitrogen likes to make 3. I'm just looking at my carbons here. This carbon, 1, 2, 3, and then 4. All right, that's good. This carbon right here, 1, 2, 3. Nitrogen coming out. It's missing a hydrogen. It needs to make 4 bonds. So you have a hydrogen there. Pointing back. This carbon right here, 1, 2, 3, 4, already has 4 bonds. That's good. This carbon right here, 1, 2, missing 2 hydrogen here and a hydrogen here. Okay. And let's see, this carbon right here, 1, 2, 3, 4. That already has 4 bonds. That's good. This carbon here, 1, 2, we're missing 1. So that has a hydrogen coming off of it. Oh, here we are again, missing a bond. So that's a hydrogen. This carbon right here, 1, 2, 3, missing a bond. So it's a hydrogen. This carbon right here, 1, 2, 3, missing a bond. So there's a hydrogen. This carbon right here, 1, 2, 3, missing a bond. So there's a hydrogen. Okay, so that's kind of just a quick analysis of the penicillin structure, and kind of looking at where, filling in our missing lone pairs and our missing hydrogens. Now, as a chemist, right, if we were just to compare those 2 structures, this one on the left where I've added all that stuff and the one on the right just looks cleaner and is easier for us to analyze. So I'm going to move over here to this structure, and I'm going to start analyzing and picking a couple atoms to look at and determining what's the hybridization state of that atom and what types of bonds are there, sigma and pi bonds. So let's first start with this carbon right here. So I'm going to look at this carbon right here. That carbon has how many electron domains? 1, 2, 3, 4 electron domains. 4 electron domains makes you tetrahedral. So this is a tetrahedral carbon. And remember, tetrahedral carbons are sp3 hybridized. Remember I said that all bonds, all single bonds are sigma bonds. So this is a sigma bond, that's a sigma bond, that's a sigma bond, and that's a sigma bond. So that carbon is an sp3 hybridized tetrahedral carbon, and it has all 4 sigma bonds coming off of it. Hold on 1 second.